So today we begin with the definition of automorphic forms. Okay, on our upper half plane with respect to a lattice. Okay, so so I have here Zn. Okay, and so this will be the weights of the Rn. Okay, maybe I can write here instead of R. It's better to use K here. K. Okay. K1, Kn, and I have M, which is inside SL2 R to the N, and I have this Z, which is inside Xn, n copies of Z. And then we first define what an automorph effector is. Okay, so I define the automorph effector. Yeah, so this is going to look like I of mz. Okay, so and so it's better to use this. Okay, so this is defined to be n of cz plus b. Okay, to the power of k. Okay, so I'll explain to you what the meaning of this is. Yeah, and so this is equal to the product of say Cj times Zj plus Dj to the power of Kj. Okay, so J equals to 1 to n. Okay, so this is one possible automorph effector, and then what one can see is that so it satisfies this cocycle condition. So then we have this that if I take M and N, two matrices inside SL2 R to the N, then M times N applied to Z can be shown to be equal to I of M comma NZ, and then I of comma Z. Okay, so this is the condition which is satisfied once I have this definition. This is the automorph effector. Okay, and we can also put other things here like a twist character and so on. Okay, now after this, what we can do is we can look at functions. Okay, which will be yeah, so invariant with respect to some kind, I mean, with respect to this automorph effector. Okay, so let me, and there will be the automorphic forms. So now I can look at functions. So a function f, which is from Xn to C. Okay, so I'm using the definition which is exactly as in the case of elliptic modular forms, such that I have f of mz to be equal to I of m comma z, which is the automorph effector, times f of z. Okay, and this is for all m. Now I take m only inside gamma. Okay, so what was our okay, so this is going to be a discrete subgroup of SL2R to the n. To the n like this. Yeah, and then so these are going to be the automorphic forms. Okay, they are going to be defined in a similar manner. Okay, then let me also describe the slashing action. So I write this down somewhere here. So that it's you can compare this with the case of elliptic modular forms. So you have here the slashing action. Slashing action, okay, of gamma. So usually you denote this by f some slash k of m z. So this will be equal to, you know, you have this I m z, yeah, then you put an inverse here, and then you have f of n times z, like this. This is the slashing action. You can check that this gives us an action of gamma on these kinds of functions on f. Okay. So this is there now. It's completely it's exactly similar to the case of elliptic modular forms. And now once I have this, we can discuss about Fourier expansions of f at the cusp. Okay. So now this one is about Fourier expansion. Oh, here's a minus k. Yeah, so the minus k is there inside now. Okay, so it's fine. Fourier expansion of f at the cusp. All right. Now, for this, it's okay. So, yeah. So for this, it's better to look a little bit more generally. Okay. So so here we are assuming that. So we are assuming that infinity is cusp. Okay. We'll worry about other cusps, but so let's start with this one of gamma. And then I have this the translations which are present inside gamma. Okay, then as I have these translations which are inside gamma. Okay, so we have the transformation law, right? So we have f of z plus a equals to f of z. Okay, and this is going to be for all a, and these a's are going to come from the translations inside gamma. Okay, and we need one more thing, which is the notion of a dual lattice. Okay, so we define dual lattice, which is this E underline check. Okay, dual by, okay, so this is so-called the trace dual. Okay, so by T underline dual. So this consists of all those elements A inside Rn, such that S of A times X belongs to Z for all X, and these X come from this. Okay, so this, remember that this is nothing but the sum of summation AI Xi I running from 1 to n. Okay, so later on when we specialize it to the Hilbert Modular group gamma k, we'll see that this is this is the trace dual. Okay, so it's related to the difference of the ring of integers. Okay, so so now what you note is that what is, so if I have if I have a, so suppose, so if I have, if I have this a z to the n. Okay, so actually there is an isomorphism from t underline to z to the n, and then if I write down its image, it's going to look like this. Okay, so for some a which is inside GR to R to the power of it. Okay, then you can, then so you check that, then this you can check that t underline dual, this will be equal to the transpose of A inverse, okay, of Z to the n. Okay, and then so I have this. Yeah. So now I'm going to talk about the Fourier expansion. Okay, and for this I need one more open subset inside R to the power inside R to the n. So okay. So I take V to be inside R to the n, okay, and I say that this is open connected, okay, and this is open, and okay, connected, and I'm going to take another domain inside this one, okay. So this V contains this D. Okay, so this is so-called the tube domain inside V. Okay, so all those Z inside C to the power of n such that Y belongs to V. Okay, the real part of these imaginary numbers has to be inside V. Okay, so it's inside this region V, the real part of. So this is called so-called the tube domain. Okay, so this is called tube domain.
So Chandrakant, there is a question. Are you assuming it to be a full lattice?
This T underline is a full lattice. I'm taking this to be the full lattice.
Okay, fine. Yeah, that was a question on the chat.
Yeah. But for the sake of definition, it is not necessary to define the dual. It is not necessary to take the full lattice.
Okay, thank you.
Yeah. So tube domain with respect to B. Okay. Then there is this lemma from complex analysis. So this is the fact that suppose if I have F to be from D to C, okay, so this is holomorphic. Okay, on D, on the tube domain D. Okay, so on the tube domain D. Okay, and let's assume that the periodicity condition. Okay, so let f of z plus a equals to f of z, and let's say that this is for all a inside my, again as before, t underline, the translations inside. Okay, then there exists a unique Fourier expansion Fourier expansion, okay, given by f of z. So this is equal to, so all these duals and so on will come here. So this is inside. So G belonging to E underline dual AG, okay, and then e to the power of say, so I'll write here, okay, so it's 2 pi I s of gz, gz. What is this E? I'll just say in a minute. So this one. Okay, so I'm just writing. I'm writing. Okay, so where E of yeah, so something I have here. This is nothing but the exponential e to the power. Okay, and then and s of gz, as I have already defined. So this will be the sum of all the coordinates which are present inside gz. Okay, so it is this, and there exists a unique Fourier expansion, okay, like this, and as is typical of Fourier expansions, we have and the series converges absolutely, okay, and also uniformly, okay, and uniformly, okay, but it doesn't happen everywhere. This is going to happen only on compact subsets, on compact subsets. Okay, so this is a general result, and so I haven't said what is the relation of the tube domain V here. Okay, so let me say that. Okay, so in that special case, so suppose if my Y comes from V, okay, yeah, if my Y comes from V, then I can determine my AG as then AG equals to, so I have this volume of P inverse. So this is going to be the fundamental parallel pipette. Okay, and then you integrate it over all, over the whole of P, and then f of z, and then you multiply it by e to the power of the negative of this 2 pi I s of gz. Okay, so I'm sorry, maybe I should have. And then dx here. So dx here. Okay, so here dx equals to dx1, dx2, and dxn. Yeah, and what are these xi's? Xi's are coming from the zi's. Okay, z equals to xi. Yeah, so zi equals to xi plus I times yi, like this, and p. Okay, so this equals to fundamental parallel packet. Okay, so fundamental parallel packet of what? So say of this D underline. Okay, so this is it, and I wish I could show this. Okay, it involves some complex analysis, but anyway, so maybe you can find this in Alphors and other places. So after this, we can make this remark that okay, so here is this remark or corollary. So remark. Okay, so if I have So let's say now I have so here the previous proposition doesn't say anything about cusp and so on. Okay, so now I try to bring in cusp here. So for that I say that I have this p bar. Okay, gamma has okay cusp at infinity. Okay, again, gamma is discrete subgroup of SL2 to the power of n. Then, yeah, so P bar has an injection into R. Yeah, so remember this. We tried to look at this in the yesterday's discussion also, and then since this is also and this also happens. D0 D dual. Okay, where A is mapped to AJ. So this projection map is injective. Okay, so for 1 less than or equal to J less than or equal to N. So this is injective. Okay, all right. And then so what is the use of saying this? Okay, it allows us to say that. So then we can say things like, you know, that A is not equal to, because it's an injective map, we are doing this. A is bigger than or equal to 0. Yeah. Then I can say things like, then I can write this one, A is bigger than 0. Okay. So because if if A were equal to 0, if A were equal to 0, then then of course this is not going to be true, and yeah, so it's because of this injectivity. And then A bigger than or equal to 0. Okay, so what does this mean? This means this is equivalent to saying AJ bigger than or equal to 0. Okay, for all j, and A bigger than 0 is equivalent to saying that AJ bigger than 0 for all j, like this. Okay, but it's a little bit it's not so easy to show that. Yeah, it's not obvious that the projection map from D underline, which is this the translation, okay, the underline gamma to R, so this is injective. It needs the discreteness of D underline. Okay, now okay, let me go down. Okay, now, so here is a definition. Okay, this is about regularity of F. Okay, again, I have gamma to be discrete subgroup. So gamma, so this is discrete subgroup. Discrete subgroup with cusp infinity. Okay, and I have F to be map from Hn to C, okay, which is periodic. So this be holomorphic, okay, and periodic with respect to the underline. This is what we need. Yeah. Then we say that F is regular. F is regular at infinity if, yeah. So this is going to be a condition on the Fourier coefficients. Okay. So if AG not equal to 0 implies that G is bigger than or equal to 0, which means that if it is non-zero, if the Fourier coefficients are non-zero, then the elements inside the dual lattice, all of them are positive. Okay, and then you say, so this is about F being regular, and then you F vanishes at infinity if um, okay, it should be regular if F is F is regular at infinity. And what is the other thing? And I need also the, if I have an A0, then this is equal to 0. Okay, so this is the condition for being a cusp when you have elliptic modular forms. Okay, so these are the two conditions which are needed. So in other words, so this is equivalent. Okay, so this is, yeah, equivalent to saying that the Fourier coefficients are non-zero. Yeah, then it happens only for G strictly positive. Okay, so as you can see that these are conditions on Fourier coefficients. Okay, conditions on Fourier coefficients of F. Okay, so with these things we can define what is what are Hilbert modular forms. But before that, to define, like for example, Hilbert modular forms which are vanishing at all the cusps, whatever we have done, we need to generalize it to arbitrary cusps. Okay, so now we have a small goal here, a short goal. Okay, so goal is to generalize this definition to arbitrary cusps. Okay, so this is the thing. So and what is the idea here? The idea here is that I will take an arbitrary cusp. I will conjugate it to the cusp at infinity. Okay, and I'm going to use the condition there. Okay, to define vanishing or regularity. Okay, so idea is to look at. Okay, consider automorphic forms. Okay, for conjugate discrete groups. Okay, so this calls for a need. Okay, so i.e., if I have F from x to the n to C, okay, so this is holomorphic, and well, it satisfies the transformation law also, and the transformation law holds. Okay, then so which means that I have f of mz equals to n of cz plus d to the 2r times f of z. Okay, now I take kappa, which is inside r to the n. This can be other cusp, but we have to look at in the closure. Okay, so this be a cusp of gamma. Okay, then let's transform it to the cusp at infinity. Okay, so let's transform this. Let us transform it to infinity by some matrix A. Okay, a kappa equals to infinity, yeah, for some a which is inside SL2 R the n, like this. Okay, then once I take this, so as I have here a kappa equals to infinity here, so it makes sense for us to look at this new automorphic form. Okay, so I'm going to just so we define, so we can define. So these are completely obvious maybe. So gamma A is this new discrete subgroup A gamma A inverse. Okay, then I also define F subscript A of Z. Okay, so this one will be defined by I of I'm going to take A inverse of Z. Okay, and then the inverse of this time. So it calls for a need to define this this new function fa. Okay, and I of a z. So where I of a z. So this is equal to again n of cz plus d to the power of k here. Before, then you can check that. Then one can check the following. So this is an easy check. Fa of mz equals to I mz, and then Fa on z. And then what is now m? So m, so this is going to, so for all m inside in this new discrete subgroup gamma A. Okay, so this is an easy check. And then so what do I see from here? So here, so maybe so we can recall that that if infinity is a cusp of gamma, then kappa is going to be a cusp of kappa is yeah. So if kappa is a cusp, then infinity is a cusp of gamma A. Okay, so here, so so here there is only one problem, and then let me highlight the problem here. So what is so we want to, so okay, so so we want, so, okay, so this is we want, okay, to define, okay, both regularity and vanishing at kappa. Okay, okay, if it is at kappa, maybe I will just insert as well. At kappa holds, if it holds for if it holds for fa, like this. Okay, but there is a problem. And what is the problem? Problem is that we need to show the independence of A. I mean, there could be two matrices A and B, which takes kappa to infinity. Okay, so here is a problem. Problem is that we need to show independence of A. Independence of the conjugating matrix A. Okay, but so let's do this calculation because we are going to use it later on. So suppose I have, okay, so let's check this if there is actually a problem or not. Okay, so suppose I have A kappa infinity, A kappa is infinity, as well as I have a matrix B, such that B kappa. Then what I can see is that then I know that from here A, B inverse, if I apply it to infinity, is this point at infinity. Okay, so what is the upshot? The upshot is that it's enough to look at matrices with fixed infinity. Yeah, I mean it's enough to take kappa is equal to infinity itself. Okay, so i.e. okay, so without loss of not without loss of generality, but it's enough to consider kappa equals to infinity and A infinity equals to infinity. Okay, so now so in that case, suppose I have A infinity to equals to infinity. Why do I want this? Because in this case, I know how to write down the matrix A. Okay, so then this implies that I can write down my matrix A as something like 1 B 0 1, and then multiplied maybe by something else. Okay, so A 0 A inverse. It has to be an element of SL2. Okay, so I need this. So my A is going to look like this. There is a plus minus 1, but we can forget it. So and now, so you take. So I take f of z, okay, and then now then I'll have a Fourier expansion Ag of E to the power of 2 pi I s of gz. I'll have this, okay, and then here G belongs to the dual lattice here, the dual translation lattice, and then let's write down for Fa and then check what happens. How does okay, and F A Z equals to G belongs to the translation lattice dual again here, and then here I have AG. So because there is an A, so we can write an A here, AG of A, okay, something like this, and then e to the power of 2 pi I s of gz. Everything is the same here. S is the trace, okay. So this is what I have. Then yeah. So now let's calculate. Okay. So where so this is with respect to, maybe we can say here dA. Okay, dA dual. Okay. So this is the place where we need this, where we need whatever we have done about. Okay. So where the translation matrix for A. Okay, so this is gamma, what was it? A gamma A inverse like this, right? A gamma A inverse, okay? And this will be equal to A times D. Okay, this is what we saw yesterday. Okay, and then this will show us that this will imply a similar thing for the underline of this A gamma A inverse 12. Okay, so this is equal to A inverse of D underline 12. Okay, so these are some simple checks. Yeah. So then if I calculate, then we see that FA of Z, so if I make these transformations here, then FA of Z will be equal to the NA to the power of minus K here, okay, and then summation of AG. So these are, I mean, G runs from E underline 12. It has a lot of notation, but e to the power of, okay, so there will be a minus here in the first case, e to the power minus 2 pi I s of G, okay, and then e to the power of 2 pi I, the trace of G, okay, square, and then Z here, like this. Okay, so this is some simple calculation which you can see from here. Now what? Now, so if I compare the Fourier coefficients, then we get, so this implies that I will have here AG of A equals to NA power of minus 2R. So this is K minus K. Okay, and then e to the power of minus, okay, so minus 2 pi I S dg times A G square. Okay, and this here G belongs to A gamma A inverse gamma. Okay, so it's the product of these three things. So AGA. All right. Now, so can I define? Can I now define vanishing? Okay. So we can now define vanishing here. Okay, because as you can see that, yeah. So let's make this formal definition, and I think everything is will be clear. So here I have this definition. So again, I have gamma to be discrete subgroup. Okay, with cusp kappa. Yeah. So let gamma be discrete subgroup with cusp kappa, and F from Hn to C holomorphic. Okay, with F of mz equals to the automorph effector times F of z. Okay, for all m inside gamma. Okay, so then I can say that F is regular at kappa if for some A inside SL2 to the n, okay, this n is outside. FA, what kind of an A are we looking at? We are looking at for some A which takes the cusp kappa to infinity, FA is regular at infinity. Now this we can say because regularity is a condition which says about AG not equal to 0 happens when, and then as you can see from here that I have an A square here. Okay, so that's why it doesn't disturb the parity of G. Okay. So similarly for cusp. Okay. and also so similarly so also f vanishes kappa if okay. So now with this we can talk about the vanishing of the regularity and the vanishing of automorphic forms. Okay, so then we can define cusp forms and so on. Okay, so here so one thing which has come from these calculations is the following, that uh, okay, so we can say that this is also a notation that if f is regular at infinity, okay, then so if f is regular at infinity, then we can define f infinity as this number a0. Okay, this is called the value of f at infinity. So these are just things which are similar to the case of elliptic modular forms. Okay, and does it allow us to define the value at other cusps? No, that's because I mean it will depend. This value is going to depend upon the choice of A. Okay, whether it is 0 or not doesn't depend upon the choice of A, but the exact value will depend upon A. Okay, though it is a non-zero factor. Okay, so here is maybe you want to call this a proposition or an observation. So that suppose if I have f to be regular, so f be regular at the cusp called kappa, or yeah, or vanishes at, or vanishes at kappa. Okay, all right. Then the same applies to all the other cusps. Okay, I didn't quite, so I just want to. So then f is regular at all cusps equivalent. Common equivalent cusps. Okay, or vanishes at all equivalent cusps. Okay, so again, so we just transform. So let me just give you this one line argument. Okay, so let me see what it takes to prove these kinds of things. So suppose I have kappa to be equivalent to infinity, right? Then I know that there exists an A. Now, so these are equivalent to, kappa is equivalent to infinity with respect to gamma, okay? Gamma equivalent. Then I will have A inside gamma, okay? Such that A kappa is equal to infinity, all right? So then this implies that F equals to Fa, right? And then this implies that Fa is regular kappa, or when this is at this cusp kappa. Okay, all right. Then should I do? Yeah. Okay, so now let's go to examples. Okay, so let's go to examples. Examples. Oh, I haven't defined what a. Have I mentioned this? Okay, so maybe first I write this definition. First I give the definition of then only it makes sense to write down the example. Okay, so here is this definition. Okay, I have gamma to be inside SL2 to the power of n. This is a discrete subgroup. Okay, such that, well, let's write everything here such that I need whatever I need. It's n star. Mod gamma is compact. Is compact, right? Then and automorphic form of weight okay, k equals to k1 kn. Okay, so this is inside z to the power of n with respect to gamma. With respect to gamma, okay, so this is a holomorphic function. A holomorphic function. Okay, a holomorphic function f from its n to c such that 1 f of mz equals to n of cz plus d to the power of k times f of z, and for all m psi gamma, and second is this regularity condition f is regular interclass. Yeah, and then we say that we say f is a cusp form f is a cusp form if f vanishes at all the cusps. All the cusps. Okay, so even if it doesn't, it vanishes at one cusp but doesn't in the other, then it's not called a cusp form. Okay, and if so, if okay, second this definition, if gamma okay is commensurable with SL2. Okay, you would have seen this definition of what a commensurable pair is. Commensurable with SL2 or K, right? Then okay, so then the automorphic form is called a Hilbert modular form. Hilbert. Okay, so so in some sense, yeah. So when I fix the discrete subgroup to be SL2 OK or finite index subgroups of SL2 OK, then we refer to these automorphic forms as Hilbert modular forms. Okay, so IE for gamma finite index subgroup of SL2 OK. Yeah. The automorphic forms are usually called Hilbert modular forms. Same thing, I'm repeating it again so that it stays. Okay. And so one thing which is nice about this is something called the Kicker-Pins principle. Okay, so maybe before we do that, we can I can give you some examples. The first thing is to ask ourselves what are examples of these automorphic forms, and then so example. Okay, let's take here the easiest case when I have k to be equal to 0, 0, 0. Okay. Then this is I'm asking what modular form Hilbert modular forms of weight 0 are. Okay. So then I have f of mz equals to, what is it? Equals to f of z, yeah, for all gamma. Okay, so this is what we have. Then so because of this condition, you can see that yeah. So let me give you a brief sketch, just a few words about what these functions are. Okay, so then what you can see is that my f, okay, so f, so this is a function on xn star mod gamma. Okay, so this happens, and suppose if it is a cusp form, right? So now what happens? So I have f, and then I have this this space. Okay, so then and this is compact on this, which is compact, Okay, so therefore, yeah, so this, we know this from complex analysis. So therefore, f has its maximum in this space. Yeah, I think it's called the maximum modulus principle, right? So But if I want my f to be a cusp form, then it has to be attained inside its n itself. Okay, so it's only a brief sketch. We have to prove other things besides this, okay, necessary things. Okay, but so then if f is cusp form, okay, then yeah, so at infinity it is finite. Then by the maximum modulus principle, so f has to be a constant, so f equals to constant, okay, and then this is equal to 0, okay. So if I have other cusps, right, then I can take this f is constant, okay, which is, and this is equal to 0, okay. So if I have other cusps, okay, so suppose if I have other cusps b1, b2, and so on up to bh. Okay, so it's not a good notation. Kappa 1, kappa 2, and so on to kappa h. Okay, so these are cusps. Then look at this function, which is f of z minus this kappa j. Okay, and then you take the product of this j equals 1 to h for each of the cusps. Okay, then this is, you can show that this is invariant with respect to gamma, and then therefore again this defines an automorphic form. Okay, so this is an automorphic form of weight 0. Okay, and then therefore it is a cusp form, and hence it is equal to 0. Okay, so it is cusp form and hence 0. Yeah, so one of these factors have to be equal to 0, but holomorphic forms which are non-zero can have only finitely many zeros, and then therefore it forces your f of z to be equal to kj. Okay, so therefore f of z equals to this j. Okay. Okay. So is this confusing? Is this kappa confusing? Okay. So
I was a bit puzzled. Like it's not the value of the at the cusps, but
it is the value. Maybe I'll use a different notation. I wanted to say that the value of so maybe I can write. Okay, so maybe I will write this kappa f of kappa 1.
Yeah. Okay.
F of kappa 2.
Okay.
I wanted to use k, but then I thought that k is the weight. So f of kappa j here. So maybe now this is better.
And of course, probably when you say f has its maximum, you probably mean mod of f, maybe.
Mod of f, yes.
Yeah.
Mod of f.
In your second line, yeah.
Yeah. Okay, so it means that automorphic forms of weight 0 are constant. So that's the thing. And then the other example is this following. So let me just. Yeah, so this is the okay. So the other example is the example of an Eisenstein series. And why do these kinds of examples come to our mind? Okay, so this is of weight, even weight, okay, 2r. Let's say it's even because we are going to look at SL2r to the n, and then yeah, so they have so there in the case of elliptic modular forms, we know that odd modular forms, odd weight, and so on. Yeah, so we are going to look at even weights. Okay, we can define this in general. Okay, it doesn't mean that we can't define it. Whenever we have those unimodular matrices, yeah, 0, 1, minus 1, 0 kind of thing, then we know that the way it transforms. Okay, so here I have again gamma. So what is the idea, okay, behind, and why do we say that these are the first examples? Is because of the following. So suppose if I have so I have this group gamma acting on a set, acting on a set X. Okay, then I want to create let's say, yeah, so this set X has got all, I mean, the properties that I can add elements here and so on, and so, yeah, so then what I can do is I want to create and I want to create a sum which is invariant when I apply gamma. Okay, so the idea is to look at this sum. I mean, maybe I can look at one element here, X, and then I apply gamma here for all elements inside gamma. Okay, then what happens is that whenever I apply another gamma, right, then this sum, okay, so let's call this sum as S. Maybe little s here. Okay, so then when I apply s again, I apply gamma for some gamma prime, then I know that this will be x gamma apply gamma prime, yeah, and then gamma runs over all gamma. But as and when gamma runs over all gamma, we can see that gamma gamma inverse also runs over all the elements of gamma itself. Then I get back s. Okay, so this is why this is, yeah. So this is why it's elementary to look at Eisenstein series, and the way we construct it is we are going to use the slashing operator. So so we are going to look at this one. So the sum E to R, okay. E to R, so this is going to be defined by, just take the element 1, okay, and apply M on this one, and then I take M inside gamma, okay, but then I remove the stabilizer of infinity, okay. I take the equivalence class with respect to infinity. Okay, so this is this will give us the Eisenstein series of weight 2r in the following sense. Okay, so so then E 2r of z, so this one will be equal to summation. I have here m belongs to gamma mod gamma infinity. So if I apply m, if I apply the slashing action on m, then I'm going to get only this one, the norm of cz plus d raised to the minus 2r. Okay, now if I have this from the way we have written, it's completely obvious that this is going to be invariant under gamma, okay, under the transformation law, and then therefore, yeah. So now, so it's clear. So clearly, E to R is invariant under gamma. Okay, so therefore this is going to be an automorphic form of weight to R. So therefore, E to R is a Hilbert modular form of weight to R. Okay, so this is equal to 2R1 to Rm. Yeah, so okay, so but we are not done because we still have to show that this sum makes sense. Okay, so and how do we do that? So so it's not very difficult. So not that. This sum. So let's just take the absolute value, gamma, mod, gamma infinity, and then the norm of this one. So I'm going to get the real part of this. So it will be the norm of Cz plus d, the power of minus 2 times sigma. Okay, but this converges in, yeah, so this converges inside this converges in Hn, yeah, so for sigma bigger than 2. So this is way. So therefore it does make sense to talk about this infinite series. It makes sense. Okay, all right. And now, so once I have this Eisenstein series, I want to know, okay, so I haven't written, but just for completeness, so we also write, so also E to R of, this is, I'm just repeating. Okay, this is holomorphic, okay? And one thing is that what is the value at infinity of this E to R? Okay, so let's calculate that. So E to R at the infinity cusp. Okay, so now this will be equal to the limit of the imaginary part, okay, E to R of Z, like this. Okay, so for this I have to calculate. Okay, so I have to calculate this one. So I have to calculate the limit of this n of Cz plus d to the power of negative 2r, okay, where converges to infinity. Yeah. So this is if my c is equal to 0, then yeah, it will be 1 because I have here e to the power minus 2r, and so this is 1 if c equals to to 0, and this is because this square is a multiplier if c is equal to 0. Okay, so this is, you can just compute this, and then this is 0 if c is not equal to 0. Okay, so so therefore the value of, at infinity of this one will be equal to 1. Yeah, when I calculate it to infinity, it will be equal to 1. Okay, so at the other cusp, it's a little bit, it's not difficult also. One can calculate it, but let me just write down. Okay, and if kappa is cusp not, okay, gamma equivalent to infinity, then this is also a limiting argument. Okay, then e to r kappa is 0. Okay, so then the proof, yeah, I mean, involves taking limits along the cusp sector and so on. So let me not just go into the details of it, but this is, but really not at all difficult. Okay. Yeah. So these are two examples, and then I have not given you an example of a cusp form. Okay, but maybe we can, it will come a little bit later. So here is this remark. Okay, so if I have a cusp, okay, so if I have kappa, cusp of gamma, then I can transform this kappa to infinity, and then it's also good to look at e to r a, okay, of z. So this will turn out to be equal to, again here, n of cz plus d, no change here, power of -2, and then sum is over belonging to a gamma mod here a gamma a inverse, and then the stabilizer of it. Okay, so this is the EA is the cusp, the automorphic form which we have defined earlier. So we are doing it for this Eisenstein series. Okay, all right. Now, any questions?
You probably mean -2r, right?
-2r. Yes. Thank you. -2r. Yeah. So now I have some. So these are some notations, I think. Yeah. So.
Chandrakant, summing over quotient is also invariant, right? Just like summing over the group, right?
Yes. Because we have removed the stabilizer, we don't want the point at infinity to be repeated again and again when we take the sum. The value at that point.
Yeah. Okay. Thank you.
Yeah. And the good thing is the following. So what have I done now? So done this. Yeah, this is fine. Actually, I did some calculations. I'm also a little bit lost. Yeah, maybe this one. So so here is a theorem. This theorem is a consequence of whatever we have done. Okay, so suppose I have it's n star 1 gamma. Okay, suppose I have this to be compact. So in case of modular group, we have already seen that this is compact. Okay, but I'm writing this in general for any discrete subgroup. Okay, so there are only finitely many cusps, and then the cusps kappa 1 and so on up to say kappa h. Okay, and let us take all of these cusps to infinity. Okay, so let a j inverse of infinity to be equal to kappa j for all the j. So j is running from 1 to infinity. Then we can look at the Eisenstein series, okay, which are which look like the above one, which I have just written. Okay, then the Eisenstein series. Okay, so here I have here E 2R of AJ now. Okay, so in the remark I have this for A, but now I have this for AJ. So let's look at this. This will be defined by this EJ. Okay, so J less than or equal to 1, less than or equal to H. So they are linearly independent. Okay, and once I have a linearly independent set, we ask if we can span the whole space. Okay, and they are linearly independent. Okay, and then they generate a vector space, which is denoted by this calligraphic E. Okay, and then this E, but we should not forget that there is a discrete subgroup in the background, and this will be nothing but the span of this E 2R of AJ offset here like this. J equals to 1 to H. Okay, and then this depends only on gamma. It doesn't depend upon our choice of A. Okay, so it depends on the subspace which is spanned by the Eisenstein series. Okay, so that's because we have seen how the coefficients transform when we change the AJ, and it doesn't affect the space with the complex span of the Eisenstein series. Okay, all right. Now, so here is this definition. Okay, so E is called the space of Eisenstein series of gamma. Okay, so the fact that it depends, as I said, only on gamma is because of the way we have constructed the Eisenstein series, and also we know how the coefficients change. Okay, so maybe maybe we can try to give a proof of this. Since it's not so difficult, we can try to give a proof of this in the discussion session tomorrow. Okay, all right. Now, so here is the thing which we have, which we wanted to see. I mean, how much does the space of Eisenstein series contribute to the space of the full space of automorphic forms? Okay, and then as before, I have, let's take gamma, which is the Swiss subgroup of SL2R to the n. Okay, which satisfies the condition that Hn star mod gamma is compact, and I have highly many cusp and so on. And then so if I have the, so if I denote the, so the full space of automorphic forms, okay, of weight, say 2R. So it decomposes as the space of cusp forms of weight 2R. Okay, so this is, and then direct sum this, the one coming from the Eisenstein series. Okay, and as we have seen, I mean, as many cusps as there are Eisenstein series in the way we have defined. Okay, so note here that the dimension of this is H. Yeah, so this is exactly as in the case of elliptic elliptic modular forms. Okay, so but the question is this, we are talking about space of automorphic forms and so on, but is this finite dimensional? That's the next question. Okay, so finite whether the space of automorphic forms really is of finite dimension and so on. So let me just, it's a very elaborate calculation, okay, to show that the space of this cusp forms is finite dimension. But let me just briefly tell you what the idea is by sticking ourselves to one condition, to a special case, okay. But the idea is there itself. So the idea is the following. So if you want to look at the most general thing, then I think it's given in Freitag's book. So here what you do is that the idea is that you compare two different norms on the space of cusp forms. Okay, so I will show you a sketch of how this is done, comparison of two different norms on this, on so maybe I can use this as S2K of gamma. Okay, so this we can use this notation, space of cusp forms. Okay, so I think in the book of Miyake, he defines the space of automorphic forms to be the fraction field of the space of modular forms. Okay. And so we give only for weight that looks like k, comma k. Okay. Also, idea is there, and then give a sketch of the proof. Sketch of the proof. Okay. So we make this restriction. Okay. So one is I look at weight that look like k comma k. Okay. K belongs to Z. And then the second is we look at n equals to 2. Okay. So we look at these cases. Okay, it's better to. I mean, I can write this better. So then, so the first thing to see is that we note that on H2. Okay, so we need other facts. Okay, so on H2 we have a differential form. We have a differential form. The mu, which I can write as dx1 dy1 by y1 squared. We have only the first factor when we look at the case of elliptic modular forms, and dx2 dy2 divided by y2 squared. Okay, and on this there is an SL2R action, SL2R2 action. Okay, so on this there is an SL2R2 action component wise. The first matrix will act on this one, the second one will act on this one. The same action as we have seen in the case of elliptic modular forms. Okay, and this is invariant SL2R action, so this is invariant action. Okay, then the proof in the case of elliptic modular forms also needs us to define the Peterson inner product. Okay, so let's begin with that an analog here. Okay, so I take F and G. Okay, so modular forms of weight, this one. Okay, so the Hilbert modular forms of weight K. Okay, so weight K comma K. Okay, such that let's assume that the product is a cusp form. This was necessary. Okay, so F such that FC is a cusp form. Okay, then how do I define the Peterson inner product? So it was defined by F comma G. Okay, and this is equal to the integral of f of z times g of z, but you take the complex conjugate here, and then you take, in the case of elliptic modular forms, you take y to the power of k, but here I will take y1 times y2 to the power of k, and then instead of just having dx1 dx this invariant differential, so we take here d mu. So this is completely analogous as, and then to the case of elliptic modular forms, and then this integral is over the fundamental domain, which I have not quite defined, but there is a fundamental domain here also. Okay, where f is a fundamental domain for gamma. Okay, all right. Now, then the first thing to check is that this integral makes sense and is independent of the choice of the fundamental domain. Yeah, there can be many choices of the fundamental domain, and then okay. So so okay. So remark. Okay. So f comma g is okay. So this converges. This integral converges absolutely, and is independent of the choice of the choice uh, of the fundamental domain. Okay, so the proof is just the gamma invariance, okay, of this integral, and it is bounded on H2. So the integral doesn't depend upon the choice of f, okay, and the absolute convergence follows from the dominated convergence theorem. These functions are going to be dominated inside the fundamental domain. Okay, so once I have this, okay, so to prove, okay, so yeah, so once I have this, yeah, so it makes sense. I can talk about the Peterson inner product, and then I can define the norm which comes from the Peterson inner product. Okay, so then, so therefore, Peterson inner product defines a scalar product, okay, on Sk gamma. Okay, so and with not and so and this inner product will give us a norm, okay, and we denote the two norm of the square root of, yeah, okay. So this is this is the first norm, okay, and the second norm is nothing but kind of a supremum norm, okay. Then so this is going to be our first norm, norm 1, okay, and then I have a norm 2 also, which is defined by, so for f inside Sk gamma, the infinity norm is going to be defined to be the supremum so f of z times y1 y2 to the power of k by 2, okay. Okay, so let's take the norm of this one. Okay, so this is the second norm. This is norm 2, and we are going to compare these two. Okay, so here is a lemma. So there exists constant A So this constant A is going to depend upon gamma and K, okay, positive, such that the infinity norm is less than or equal to A times the 2 norm, okay, the 2 norm of F. And this is for all F inside SK gamma here. Okay, so this is an estimation. I'm not going to give proof of this. So here, the only word which I can mention is that the Fourier expansions of F, using the Fourier expansions of F at the cusp of gamma, we can estimate the L2 norm. Okay, but again, here we are going to do this along Ziegler domains. Okay, so you can find the proof of this, I think, in Freitag, though he considers it in a much more general case when I have any gamma here, discrete subgroup other than SL2. Okay, all right. So, but we are going to use this one, so a proof of this can be found. So, proof it involves uh, estimate of Fourier coefficients, okay. So for this we have to look at Fourier expansions of F at all the cusps of gamma, okay, and then for the integral part you have to look at those Ziegler domains, okay. All right, so I just leave it here, but you can look at, I think,